In this part, we're going to expand upon what we did in the previous part where we had our simplified shading for our painterly post-processing. In this part, we're going to begin by adding brush strokes. However, we can't just apply a brush texture directly onto this because then it won't follow the direction of the surfaces. And if we were to move our camera around in our scene, then that brush texture would slide along. So what we want is a way of taking every object in our scene, generating some form of UVs, and applying a texture onto everything. The way we're going to do this is through triplanar projection. The way that we can think about triplanar projection is as if we were taking an entire scene, figuring out which direction a piece of geometry is facing in, and then projecting UVs from that direction. It's generally used for things like terrain, where you don't really want to UV unwrap your terrain, you just want something that's a bit more procedural. So you'd want something where you could take your position in world space, convert it to UV coordinates, and then apply a texture using that. Now, this will work as long as the objects in your scene aren't moving. If you do have moving objects in your scene, you'll have to do something different. You can use something like UVs in that case. So anything that's static in your scene, you can do triplanar projection. Otherwise, it would be recommended to use a UV map. So for this, we're going to need a few more render variables. As you can see, we already have these that are created. But as I mentioned before, these only exist within the context of Houdini. As soon as we render out, these will be discarded and it'll only keep our color value. So how do we actually define AOVs? We can use an additional render vars node, and this will allow us to add additional render vars. So I'm just going to clear the one that's there. And the way that this works is actually with a comma render node. So if we drop a comma render node, such as comma, we'll take our camera into first input and our additional render vars into second input. This is because this is the node that actually processes these additional render vars. So I'm going to switch our comma render settings to use XPU. Then we're going to go over to the image output, and under our AOVs or render vars, import our render vars from second input. Now, any sort of additional render variables that we add using this node will now be processed by our comma render settings node. So let's go over here and add one. So we can add P for world space. And if we take a look, we now have position, right? So position is now being saved out as a render output. Let's go ahead and add a few others. So I'm going to add another one over here. And this one is simply going to be our smooth normals. So N smooth normal. Again, if we render, you can see what this looks like. And that's actually all we need. We only need our position and our normals, and that's going to allow us to do triplanar projection. So go back into your comp node, and with the slap comp import, just say add AOVs from last render. This will add all of these extra ones. Now, you will see that it added all of these other ones that we don't really need. We'll keep them there for now, but I'll address the issue that this causes a little bit later. Now, there are multiple ways to do what I am about to show you. You can do this with OpenCL, you can do it with nodes. I'm going to do it with a wrangle right over here. So this wrangle is going to take a few things. We're going to need it to take our normals. So we can put in N over here, switching it to RGB, bring in N, and now we have access to a variable called N. We can add another one, and you will notice something. As soon as I type P, it'll throw an error. So if I switch my display flag, you'll see that there's an error. It says internal value P already exists. So there's a conflict of names. So you can rename this to something like pos, and that'll be fine. Then just plug P into pos. And the last thing that we need is a third one, which is going to be a type of UV. And the binding name is just going to be UV. So these are going to be the UVs that we output from this wrangle. So firstly, we want to find the projection from every axis. So that means we want to find the projection from the x-axis, the projection from the y-axis, and the projection from the z-axis. Another way of thinking about this, which I can very quickly show you over on the object level, is if we have a grid, so we just have a grid, if this grid exists on the zx plane, then when we look from the y-axis, we're perpendicular to it. If we're looking from the yz plane, then if we look from the x-axis, we're perpendicular to it. And if we look from the xy plane, if we're looking from the z-axis, we're perpendicular to it. That just means that we're projecting along the axis that is missing from this, right? So in xy, z is missing, so that means we're projecting along z. In yz, we're projecting along x. In zx, we're projecting along y. So that means that in here, we're going to want a few vector 2s. The vector 2s that we're going to want is just uv underscore zy, uv underscore xz, and uv underscore xy, right? So this is each projection. This is the x projection, y projection, z projection. And now the way that we're going to find each one of these is by doing uv underscore zy equals set. And inside of here, we're going to be taking our position of those two components. So we can say at pos dot z, comma, at pos dot y. So I hope you can see that all we're doing is we're taking our position that we're inputting into this wrangle. We're creating a vector 2, which represents that projection's direction. So I'm going to copy this over, and we can just make adjustments. So this one is going to be xz, this one is going to be xy. And then we just have to fill in the components as well. So x and z, x and y. If we were to now say at uv equals, let's say uv underscore zy, and apply this and accept, we now have access to a projection along that particular axis. So in our case, we've said that uv is equal to uv underscore zy. So this is our x projection. So let's see what this looks like. If we use a tile pattern, that's going to be the easiest way to view this. And then we're going to use a texture sample. A texture sample simply takes an image. So we're going to take our tiles into the texture input and our UVs into the UV input. And let's see what we have. As you can see, we have a projection along the x-axis. If we were to change this, so to xz, that's the projection along the y-axis, and then xy is the projection along the z-axis. Right, so you'll see that it's all weird on most axes, except the side of the box. That's because that side is facing quite closely along the z-axis. So now that we have these three projections, we need a way of blending between them, right? Because each one of these are correct, but only in a particular direction. We want to blend between them based on which one best applies to a particular geometry based on its normals. The way we're going to be doing this is by weighting each one of these based on the geometry normals. So let's go back into our wrangle over here, and we're going to add a couple more things. Let's go ahead and add a couple of floats, and these are going to be for our weights. So we're going to do weight underscore x, comma, weight underscore y, comma, weight underscore z, and we're going to have a final one, which is going to be our cumulative weight, so weight total. Now, the way that we're going to find the weightings for each one of these is by using the absolute value of our normals, because it doesn't really matter if we're looking at the top of the box or the bottom of the box. The projection in the y-axis applies to the top and the bottom, so that's why we want the absolute of our normal values. So we're going to say that weight underscore x is equal to at n dot x. And we're going to make that absolute, so put this in brackets, just like that, absolute of at n dot x. We're going to do this for the other three. So we're going to have weight y, n dot y, weight z, n dot z. Now we want to add all three of these together and then divide each one by the total. That's going to give us normalized weights. So we go weight underscore total equals weight underscore x plus weight underscore y plus weight underscore z. Then divide each one of these by that weight total. So again, that's going to be weight underscore x, divide equals by the weight total, and that's going to be done for each one. So again, I can just copy and paste this, y and z. Okay, so quickly going over this again, we're just creating four variables over here. One is our weight for the x, weight for y, weight for z, and the total weight. We then make the weights for x, y, and z equal to the absolute value of each of the normal directions on those axes. We then add all of that together, because this allows us to find the normalized values by dividing each one of those weights by the weight total. Once we have that, finding our UVs is quite simple. All we have to do is say at UV equals, and then multiply each one of our UVs by their weight. So that'll be UV underscore ZY multiplied by weight underscore X. And again, keeping in mind that the missing component over here is the one whose weight we want to fetch. So this is ZY, which means X is missing, so we multiply it by the X weighting. Then we add that to the same thing for Y and Z. So UV underscore XZ multiplied by weight underscore Y plus UV underscore XY multiplied by weight underscore Z, semicolon. If we apply and accept, and then take a look at what this looks like, you'll see that it looks a bit messy. And that's simply because there isn't perfect alignment occurring for every axis. So the way that we're going to work around this is by narrowing in the values for our three various weights. What's happening here is that it's blending too much between two axes as opposed to finding an axis that fits most closely. The way that we can improve this is by putting each one of these to the power of some value. So if we go power of, let's say, 10, and then do the same for all of them, you'll see that it fits more tightly. And we can increase this value even further, to something like 50. At some point, pushing this up any further will cause issues, but as you can see, this works quite nicely. The lines now fit against our geometry as we would expect them to. Now, you will notice that there is a seam, and that is, of course, going to happen with triplanar projection. Now, this is a fairly simple triplanar projection in that we're simply projecting along three axes and then weighting each one accordingly. There are other ways you can actually project in more than just these three axes, or you can even use things like occlusion to define where these seams are. We're not going to go into all of that. For now, this is all we really need. I just want to show you that this works as an output. So if we output it over here into our block end and go up a level and enable it, it will appear as red. And that's simply because this is a single channel. So it's showing as red. We can convert this. So we can go mono to RGB or mono to RGBA. And then go up a level. And as you can see, these lines are now sticking to our geometry. So no matter how we move around in our scene, these lines are sticking to our geometry. So I found that this is a really cool approach for applying textures to an entire scene where you don't necessarily have UVs, or you just don't want to use the UVs that are available. So now, how are we actually going to use this? Well, what we can now do is we can now apply a brush texture to our entire scene. The way we're going to do this is with a file, and I have a texture that I've created, which is just simply a brush. So if we take a look at it, it's just this messy brushstroke pattern. And instead of the tile pattern, we can use that. So as you can see, this brushstroke is being applied all over our scene. But we're not going to be using it as the output to our block end, so we can just delete this. What we are going to be doing is we're going to be distorting our simplified shading that we have over here by this texture sample. So we can use a slope direction, and this is going to take a mono output. So we can just change the brush channel type to mono. This will give us a mono output. Plug this into the slope direction over here. And now we can distort our simplified shading by that. So use a distort node, plug that into first input, and I'll distort into second input. And you'll see that it distorts it. Now that may be a bit too much, so we can make adjustments to the slope direction over here. Firstly, increasing the kernel size will give you a slightly smoother brush stroke, and then we can decrease the scale on this. So on the distort, you can now see that we can control the amount of distortion using our slope direction. Right, so it's being distorted in these various brush stroke directions. So we can plug this into our C output for our block end. And now if we go up a level to our scene view, we now have those brush strokes being applied to our entire scene. We can switch off our slap comp or switch it back on and just easily toggle between these two. Now, there are still further adjustments to be made over here. For example, we can take our texture sample that we have. We can use a normal from height. So this is a height to normal node, plugging in our texture sample. This gives us these normals. So it gives us these really nice looking brush strokes. And then we can use a light node, plugging this into N. Now the light node applies a light based on the normals to a particular input. The input that we're going to use is just a constant. And the constant value over here, we can set it to 0.5. And this is just 50% gray. So that when we apply our light, it's applied to a 50% gray constant. Now you'll see that the size is wrong. All we have to do is plug our height to normal into the source. That'll keep it in the ratio of our render. And I'll change the direction of the light. I find that one from above looks pretty good. Something like that. And then we're going to use a blend node, plugging the light into second input. So after our distort, over here, we can now try different operations. For example, screen will do that for you. But I quite like the way that dodge looks. So we'll use dodge and then decrease the amount. So you can find a sweet spot for where we have these sort of brush strokes. Now, the other thing that you may want to do, which is very common for this sort of render, is just use a Kuwahara filter. So after your distort, you can use a Kuwahara filter. And this is a sort of blurring that blurs in patches. So as you increase this value, you'll see that it further increases that look of stylization. So we push that up slightly, and that's what we end up with. Now keep in mind that you can still make all sorts of adjustments after this simplified shading node. One thing that might be interesting is to add some outlines, or to even add things like chromatic aberration. So let's go ahead and add some outlines. And we can do this with an edge detect by normal. So because we have our normal layer being output, we can take this into the normals, and that will give us these edges, increasing the edge thickness scale, decreasing the tolerance slightly blurring it. And then we can once again use a blend node, once again disabling alpha. We don't want it affecting alpha. And let's dodge once more. So we'll use dodge. You can also use something like a screen, but I like the way that the dodge looks. So we just use a dodge over there. This adds this light outline to everything. And let's also use some chromatic aberration, decreasing the amount of distortion, but increasing the amount of aberration. Something like that. And let's also add a glow to this. So we'll add our glow before we actually go into our simplification. So glow over here, increasing the threshold, decreasing the scale. There we go. And then we put it through our distort, our Kuwahara filter, and our brush strokes. One more thing that you can do is you can also take this and screen that over. So if we were to use another blend node, you can either put it before the Kuwahara filter or after. And each one will give you a different look. But let's say we want to do an overlay. Right, we can now have these brush strokes applied onto our geometry. So you can do an overlay, you can do a burn, so it's only darkening. As you can see, it adds these nice brush strokes to the surfaces of your geometry, and they do stick to the geometry surface. So if you rotate around in your scene, it will appear as if they are a texture that's been applied to your particular geometry. Now, one thing you will notice is this tiling in the background, and that's simply caused over here because we don't have any sort of workaround to avoid these seams. There are ways to fix this. I'll give you a quick example. What we can do is a UV transform node, plugging in our UVs. And over here, we can give them a rotation, perhaps an increase of scale, and then we can blend between these two. So we blend between each one of these. And if we go to our texture sample, you can see that if we blend between these two, then we have some variation, but we can use a noise pattern to blend between those. So we can use a 3D noise, so fractal noise 3D. The reason we're using a 3D noise is because we want to use our position as a seeding value so that it always sticks to our surface. It will also need a size reference. You can feed anything from your block begin into that. That'll just scale it to the correct size. And then use that as a mask between these two, and you'll see that it gives you this issue. That's simply because you don't want values that are halfway between. You want either black or white. So use a remap node and then just bring these two right up against each other, right? Something like that. And then you can go ahead and make adjustments to this noise size. And this is the sort of masking that we're ending up with. And now when we sample, it's very difficult to see where the repetition is occurring. So now if we go back over here, it looks pretty good. So there we go. That's how we can apply a slap comp for a painterly post-processing effect. Now, if you were to render this to disk, it's extremely simple to actually get this working. All you have to do is go over to your USD render up at the bottom, go to slap comp, add a slap comp, set the source to cop network, and this is looking for the output node. So it's looking for the block end over here. So all you have to do is press Ctrl C and paste that reference over here to the cop node that you're looking for. So now when we render to disk, it will apply this to our comp. However, if you go ahead and try to render this as is, it won't work. This is something that I mentioned earlier. Any of these sort of assumed AOVs will cause an issue when you try to render to disk. And so if an AOV hasn't been explicitly mentioned here, so either P or N or C, because C is the default, then you actually need to remove it from this block begin, because it'll look for it and it won't find it, and then it'll fail. So we need to remove depth, we need to remove prim ID, instance ID, and then do the same over here. So instance ID, prim ID, and depth. So we only have those three. And then over here where we're outputting depth, delete that and remove it from our block end, right? So we're only working with the AOVs that we actually have, right? We have C, N, and P, and our output is only C. So this will make sure that it works if you do try outputting it directly to disk. So that, along with the slab comp under the husk settings, will allow you to render it to disk directly. So if I go ahead and just say render to disk, we can take a look at what that looks like. And once that's done, you can see over here that it's applied this to our scene. So there we go. We've directly applied a painterly post-processing effect onto our scene and then output that to disk. So that is all for this video. In the next video, I'm going to be showing you how we can actually take a live plate and apply elements onto that plate using the slab comp process that we looked at in this part. We will once again be looking at the various layers, but I'll also be showing you how we can use the background plate node to bring in further AOVs that we can work with for compositing at the Copernicus level. So I'll see you in that video. Bye.